A lot of you are wondering why he's wearing a tuxedo. When you have a fancy name like that and you went to school at Yale, you have to wear a tuxedo for your dissertation. Most of you know George, and you know that this is not normally how he dresses. So it's my pleasure to introduce him and to tell you a little bit about him. I remember when he arrived from Yale, he asked to join my group and told me that he had been on the solar car racing team and the team had done really well. And I asked him to give a presentation to my group, and he showed me the design of the car and explained it in exquisite detail, and explained how he and the team had made all the decisions, and he explained how he had made various aspects of the car, put the solar cells down and done the electronics, and described all the things he had done in the machine shop. And even though we don't use solar cells in my group, we make them, so it's very different kind of stuff from what he had done with the team there. But it was clear that George could see the big picture and that he had an incredible amount of talent for designing and building equipment and scientific apparatus. And as all professors know, you want to have someone like that in your group. And so I was glad to have George join us. I really wish we had a picture of the lab before George came and a picture of the lab today. There's been an incredible transformation, and he's maintained a lot of equipment, improved it. I think my favorite is he got frustrated with the way we were clamping samples in the evaporator and ordered parts from a bicycle company and put them in there, and now we have a much better way for securing the metal sources. And he and Eric Hoke have just absolutely overhauled our optics lab, installing lots of very sophisticated equipment and getting it to run smoothly. And everyone in my group and quite a number of people from other groups come in and make their measurements very, very efficiently now, and so a lot of people owe thanks to George. He's going to talk about a series of experiments relating to recombination and quantum efficiency measurements in a certain kind of solar cell, but he also has a couple papers with other people where they've come and used all of this equipment. He's got some papers with the Each Way group on silicon solar cells. And I know Whitney is in the audience somewhere. Whitney and George got a paper accepted to Advanced Materials yesterday on solar nanowire electrodes and using those for solar cells. So George has done quite a number of things that no one in my group has ever done, wearing a tuxedo to his defense being one of them. He's the only one I know of to melt a screwdriver. An experiment. It's an interesting story you might want to ask him about. He's the only one to snap a carbon fiber bicycle completely in half. And he's done something I'm not too happy about. He's the only one to beat me up over the Honda. But I may still graduate it anyway.
Thank you, Mike, for the introduction and the kind words. And thank you all for coming to hear about my research of the past few years, which has been on mainly focusing on exciton recombination in bulk heterojunction organic solar cells. So to give you an idea of, of course my pointer's not working now. To give you an idea of what I'll be covering to keep everything on track, I've provided a little outline here. First, I'll introduce the motivation for this research and why our lab focuses on solar cells in general, along with some background information required to understand the solar cell physics I'll be talking about. I'll then go into a method we developed to accurately measure internal quantum efficiency in solar cells. Then I'll talk about how, using that method, we've discovered a new type of recombination that's happening in the most studied solar cells, which P3HT, PCBM solar cells. Sorry about that. And then I'll go over some implications for recombination in other types of materials. So first of all, why does our group study solar? The answer is pretty obvious. The energy usage of the world has been going up pretty steadily since the early 1900s, with 2010 energy usage at around 16 terawatts, projected usage up to 25 terawatts continuous power consumption in the world by 2040. And this has actually been increasing at a greater rate in Asia recently. And as the economy shifts to Asia, this curve might even go at a steeper slope. So there's definitely an increased need for energy in the world. And right now, 80 to 90% of it comes from fossil fuels, with 33% coming from oil. And those supplies are dwindling. So it's clear that we need a renewable solution to energy production. So I've listed the 4 most common types of renewable energy sources on the right plot here, with hydro and geothermal, both. This is the total available power in the world if you used all the available hydroelectric power, geothermal power, wind, and solar. So you can see right now that hydro and geothermal together even cannot supply the amount of power required for world consumption. Additionally, hydroelectric and wind both have environmental impacts, including damming of rivers and damage to ecological systems like fish and birds. So given the amount of power available in the solar spectrum and given the environmental friendliness of it, it seems to be the obvious choice for an alternative energy source in the future. The reason we haven't gotten there yet is because the most common solar technology, silicon solar, has been decreasing in price and has become increasingly tuned since the 1960s. But at the end of the day, the processes required to make silicon solar cells are just too expensive. They need to be formed in high vacuum and at high temperatures, and all these things are energy intensive. And so unless environmental costs are considered when factoring in the costs of coal and oil, silicon solar will never be competitive in a price market. So we're doing research on polymer solar cells. These are plastic semiconductor solar cells. They have several advantages over silicon solar cells, including the fact that they are made from abundant materials. These are all materials able to be synthesized in synthetic chemist labs, made from carbon, hydrogen, oxygen, and sulfur, and some other commonly available elements. All that stuff is really well understood and can be done in great mass. In fact, some of the solar cells, not ones I'll talk about today, but some of the solar cells that are currently being studied use the same stuff that's on your car. It's car paint. And obviously that can be made very cheaply. Furthermore, it can be produced without high vacuum and without high temperature in roll-to-roll processing, just like newspapers are printed. And they can also be made to be flexible. So they have a lot of advantages in terms of niche markets because of that flexibility. And so what's holding it back right now is that although current world record efficiencies have been increasing and they're now currently 8.3%, that's just not quite efficient enough. And so what I've been studying is what kinds of loss mechanisms there are in these solar cells that are preventing efficiencies from being higher. And it's also worth noting that right now lifetime is 80% of the original power over 6.2 years, which is a new figure that some of my lab mates just discovered. And although this is quite good, typical silicon solar cell warranties are required to be 30 years, so there still needs to be improvement with lifetime as well. So I'll go over quickly how organic solar cells work. We have a heterojunction in organic solar cells, which is a junction between 2 different materials that have different chemical potentials. So I'll show energy here, and this is just basically a position coordinate. What happens is a photon can come into the cell and excite an electron from the ground state to an excited state. And because organic materials have very low dielectric constants, the excited state electron and hole are still bound because of their Coulombic attraction, because the dielectric constant is small enough that they're not effectively screened from each other. So in organic solar cells, we deal with excitons after excitation, and this is the reason for the heterojunction. After the excitons are formed, they diffuse around through random thermal motion, and eventually we'll reach the heterojunction interface, where because of the chemical potential offset, the electron can be charged, or can be transferred into the acceptor material. It's also worth noting that you can also absorb light in the acceptor and similarly transfer a hole from the acceptor into the donor. After you have this charge transfer take place, we have almost free electrons and holes. With some thermal energy added, they can separate, and with an applied field, they can be pulled out of the device to be collected at the electrodes where they can do work in an external circuit. So most of this talk is going to deal with exciton recombinations. It's worth going over how that happens. There are two different types, radiative and non-radiative exciton recombination. Radiative recombination is basically inverse of absorption, where you form the exciton and then with some probability it'll just recombine, emitting the photon again. And non-radiative recombinations include internal conversion, which is basically the same process except instead of emitting a photon, the energy is dissipated as heat. And Auger recombination, which is a little bit more complicated. The exciton actually can couple its energy to a carrier nearby, transferring the energy to the carrier, promoting it higher up in the band. And because there's all these states up here, the carrier can quickly thermalize back down to the band edge, again dissipating its energy as heat. There's also charge carrier recombination. Once we separate these charges, they can also recombine. There are three main types that will be of concern to this talk. Geminate recombination, as the name implies, comes from the Latin term Gemini, concerns the recombination of the initially formed electron and hole. After the exciton is split at the heterojunction interface, there's some probability that the electron and hole will be separated, but there's also some probability that they'll immediately recombine. And this probability is simply just a constant probability, so that the rate of excitons that recombine via, or charges that recombine via geminate recombination is simply that rate times the density of excitons that formed those charges. So this rate has a power of 1 on the term that concerns the exciton density, and therefore it's termed monomolecular for the exponent of 1. Langevin recombination concerns recombination of free charges in the device. Now these free charges are being pulled out by the field, but there's also some probability that they will meet at a heterojunction, and in the same way these charges recombine, they can recombine across that junction. The difference here is that because they're free charges, the rate is determined by the density of the holes and the electrons, because they both have to find each other. It's a two-body process, and therefore, because we can relate the electron and hole densities, it basically goes as the square of one of those densities. This is a two-body process, and it's termed bimolecular. The last type I'll talk about is Shockley-Reed-Hall recombination, which concerns recombination of an electron in a hole, except that one of those carriers is trapped in an energetic trap. And basically, there are some population of traps in the device. Under steady-state conditions where there are free electrons and holes, as they're diffusing through the device, or drifting through the device, they will fill up the traps, and the number of trapped carriers is therefore determined by the number of traps available. So in this case, even though it's a two-body process, the number of traps doesn't change with light intensity or with generation rate, because all those traps are filled and all the transport happens below that energy, or above that energy. And therefore, the recombination goes as just the carrier density to the first power, because the number of traps is a constant. So that's also a monomolecular process. Most of the talk will focus on exciton diffusion. This is basically how far the exciton will move over time because of Brownian motion before it decays. And it's not quite true, but it can be approximated in the ideal sense as going as the square root of the diffusivity times the lifetime of the exciton. It's typically around 5 nanometers for most polymer systems that we'll be talking about. And the exciton diffusion length can actually be measured through an experiment where we look at photoluminescence quenching on either a non-quenching substrate like glass or a quenching substrate like anything that can accept an electron from the exciton. And the idea is we shine light on the material, we form excitons everywhere. Some of those excitons will diffuse to the interface with the quencher, and if that quencher can accept electrons from the excitons, then the excitons will split there and they won't emit light. Versus if you put it on glass, those excitons can't transfer electrons to glass and they will always emit. And so by changing the thickness of that film on top, we can compare the emission from both cases and with some math and some modeling, back out what the exciton diffusion length is. So it's important to note that the most efficient polymers used in these solar cells typically have very low photoluminescence efficiencies, meaning if you shine light on a pure film, the number of photons emitted by the film as the excitons recombine is much less than the number of photons that you shine on the film. And that is indicative of a non-radiative recombination process that's competing with a radiative recombination process. As I've shown here, if you look at the rates of the different processes, this one here would be the ideal radiative recombination rate. This is the rate of some non-radiative recombination process. And if we look at the total lifetime of the exciton, because of these two recombination processes that are competing, we'd get this red curve here, which is much shorter lifetime than the ideal natural lifetime of the exciton, the amount of time it would take before it emitted light and recombined on its own. Now, because the exciton diffusion length goes as the square of the lifetime, or the square root of the lifetime, we can see that if somehow we could turn off this non-radiative process, increasing the lifetime to the natural lifetime of the exciton, we'd be able to increase the diffusion length of the exciton. And that'll be important for these solar cells because, well, when we think of the solar cells, we think of a stack of materials, and the first thing that comes to mind, of course, is a bilayer cell, where we have the donor on one side and the acceptor on the other. This is not actually very efficient because the only excitons we can harvest at this heterojunction interface are the ones that are within a diffusion length from that interface. And as I mentioned before, the diffusion length is typically 5 nanometers, which means there's not very much material here that's going to contribute to photocurrent. Furthermore, in this architecture, all the charge that is transported to the material is separated. So all the electrons are on the acceptor side, all the holes are on the donor side. And as we separate those electrons, we have space charge build up. There's there's electrons here and holes here that opposes the applied electric field. So the solution to this process is the bulk heterojunction, which will be basically what I'm talking about for the rest of the talk. In this structure, the donor and acceptor are blended and phase separate on a nanoscale, so that any excitons formed in the donor, for instance, will be within, ideally, a diffusion length from an acceptor molecule. And similarly, all the electrons and holes are spread out through the device. So the space charge problem is not there, and also we can harvest a lot more of the excitons that are formed because they're all within the diffusion length of an interface. So a typical polymer solar cell architecture is shown here. These are all very thin layers, first of all, and that's going to be important. But we have a whole collector on top. It's transparent. It's the same stuff that you have in your LCD screens. It's called indium tin oxide. It's modified with a work function modifier, P.PSS. It's a doped polymer. It's not really important to know anything beyond that. The active material is that bulk heterojunction I was talking about before, the polymer and the acceptor, which in most cases is a fullerene molecule. And then there's a metal electron which collects electrodes. A metal electrode which collects electrons. And there's also a reflective contact. So what happens is the light comes in through the top here. Some of it gets absorbed in these transparent conducting electrodes because they're not quite transparent. Nothing is quite ideal. Most of it gets absorbed in this active layer, and then most of the light will bounce off the metal electrode and come back out and be absorbed on the way out as well in those layers. So that's basically the background information. Now I'll talk about this measurement I mentioned earlier about internal quantum efficiency, which I'll refer to as IQE in the future. So IQE is an important measurement because it isolates first of all, it is the ratio of charges extracted from the device per photons absorbed in the active materials in the device. And it's really important because it characterizes all the electrical characteristics of the device independently of the optical characteristics because we're normalizing by the absorption. And I've also written this charges extracted as the external quantum efficiency, which is the same sort of idea. It's the ratio of charges collected to the number of photons incident in the device. So when I mention EQE, that'll be including the absorption characteristics. When I mention IQE, it's the solar cell's electrical characteristics only. And the IQE is very useful because there are a number of reasons that a solar cell might not produce very much current. Like for one, it could be very thin and not absorb very much light, but the electrical characteristics could be perfect. So it's nice to be able to separate those out. And again, only the this is a measure of how well the solar cell is performing compared to how well it could perform. So only the photons absorbed in the active material are important here. Now it turns out IQE can also identify some unique and novel effects that are of interest to people in literature recently, including multiple exciton generation and singlet exciton fission processes, both of which can turn single excitons into multiple excitons through some quantum interactions. And the interesting thing about this is that you can actually get greater than 100% IQE because you turn one single exciton to two triplet excitons, you can pull out 2 charge carriers for every 1 photon absorbed. And you'd be interested in seeing a spectrum like this where you get a transition once you get to twice the energy of the material, where you get 200% internal quantum efficiency. So ideally, because we're normalizing by the absorption, the IQE should be wavelength independent. And it's worth noting that the only way we would get wavelength dependence is if there's a difference between the absorption in the donor and the acceptor. Because whether or not we excite an electron in the donor and form this charge transfer state, or if we excite an electron in the acceptor, once the exciton diffusion happens and the charge is separated, this is the exact same state in both cases. So once those charges are split, the solar cell doesn't know any difference about it. So any changes, any wavelength dependence of the IQE, barring some special cases, should only result from the fact that excitons are not harvested as efficiently in one material versus the other. So the motivation for this method being developed was that when you look in the literature, all of the IQE spectra do not show wavelength independence. They all have some kind of crazy signatures of the absorption spectrum of the cell. And this sort of indicates that something must be wrong with the way people are measuring the absorption of that active layer, because the external quantum efficiency is actually pretty easy to identify. The big error that happens is that people think the ITO, or all the transparent electrodes, and the reflective metal contact are both lossless. Like, they're transparent so they don't absorb. And similarly, this is a metal contact. It's a really good mirror, so it reflects most of the light, and we can just ignore the absorption of those materials. But as you can see here, this plot shows the total absorption of the device, the active layer absorption, and the parasitic absorption in these transparent electrodes. This parasitic absorption is actually pretty significant, ranging from 5% at the minimum up to as much as 35% in the areas where the active layer doesn't absorb very much. So it can't really be neglected. Furthermore, another common misconception is that because of this metal contact, the light waves pass in and then they get reflected out. So basically, a reasonable way to measure the absorption would be to take the absorption of the films on a glass substrate and simply double the optical density, because there's 2 paths. However, this does ignore interference effects. And like I said earlier, these devices are pretty thin, and therefore interference effects will matter, because you only get 1 or 2 interference peaks inside the whole cell's total thickness. And because of differences in the layers as you go up in the cell, the position of these peaks matters for the total absorption in the cell. So those effects cannot be neglected. The most common, it's also important that when actually measuring the absorption, that the measurement be taken inside of an integrating sphere and not simply measuring the spectral reflection of the device. This is often overlooked. The main reason is that despite the film's apparent transparent optical qualities, there's actually a lot of scattering that goes on. So light that gets reflected off of the back reflector gets scattered as it comes out. And so if you only measure the spectral reflection off the cell, you're only getting a small portion of the light that gets reflected off, and you'll overestimate the absorption of the cell, as shown in this graph. The solid line shows what you would measure if you only measured the spectral reflection, and the dashed line shows you the true reflection curve when measured in the integrating sphere. So the most common, or the most effective method that people have used prior to this method to characterize the active layer absorption is to simply model it all in a computer program using optical constants for each layer and using a system of transfer matrices to characterize the reflection and transmission coefficients at each interface in the stack, and also the absorption in each layer of the stack. So it does take into account all the interfaces in the layers. It's more accurate in that sense, but it also requires precise knowledge of the optical constants N and K. And this is difficult to characterize for these anisotropic polymer films, especially when the active layer is a blend of two different materials. And because of that, the transfer matrix method, when used to predict the total reflectance spectrum of a cell, does not accurately predict that. It has a general shape, but there's extra features here that are not present in the cell. And you can imagine if you use this to determine IQE, you would end up with wavelength dependence of the spectrum because of those inaccuracies. And the main reason or there's two main reasons. One, these indices of refraction vary with thickness in these polymer cells because of differences in materials as they're deposited on the substrate. There's vertical phase segregation. The phases have different orientations and different domain sizes as they progress up in the film. And also, the surface is not perfectly planar. So there is the scattering I mentioned earlier, and also because of differences in thicknesses, the interference effects can kind of get washed out when you look at the bulk reflection properties. So what we determined to be the best way is kind of a mixture of the two, a mixture of the best of both worlds. Because the active layer composes most of the reflection, the total absorption, sorry. We want to measure the total reflection experimentally and then simulate only the absorption in those parasitically absorbing transparent layers I measured earlier. And you can subtract those two to get a more accurate absorption spectrum for the material. As you can see, because the active layer consists, in the region of interest where the solar cell is producing the most current, the active layer is doing most of the absorption. So by measuring the total absorption experimentally, we do capture most of those features in the active absorption. If the error in the parasitic absorption that we model is small, it's correspondingly smaller when we subtract it from the experimentally measured total absorption. So that if you had a 10% error in the parasitic absorption, it results in roughly a 1% error in the calculated active layer absorption, because the active layer absorption is typically 90% of the total absorption. As a demonstration of the robustness of this method, I've made two plots here on the right showing what we would use if we used the method to calculate the active layer absorption using the true optical constants of the material in the transfer matrix model to calculate those parasitic absorptions, and also just setting them all equal to n equals 2. And you can see that because most of the data is coming from the experimentally measured total absorption, it's very insensitive to errors in those optical constants, which are the things that are both hard to measure and also vary with depth in these films. So this robustness allows for a lot more error in the measurement without affecting the result. And the result is we published the first wavelength-independent IQE curves. This plot shows curves for both P3HT, PCBM, calcium chloroform, and at the time, the world record efficiency materials, PCD-TBT, PC7-DBM, calcium dichlorobenzene. So the other aspect of this, of course, is the EQE measurement, which is the numerator of that IQE. And it's important to do this correctly, too. It's not hard to make a measurement that's noise-free and accurate, but it's important that this measurement be done under operating conditions, the same kind of conditions that the solar cell would see out in the sun. So we use a white light bias to shine on the solar cell during the measurement to ensure that the number of carriers in the device reflects the true number of carriers it would have in the sun. We look at the modulation of a monochromatic white light source on that solar cell. So there's a small perturbation on top. We measure that with a transimpedance amplifier and a lock-in amplifier and look at that response. And using this technique, we have basically 3 different knobs we can turn to characterize recombination in the cells. We can tune the wavelength with the monochromator. We can tune the bias in the cell with this transimpedance amplifier. And we can also adjust the light bias on the cell to change the carrier generation in the cell. And all those knobs will be useful for characterizing recombination, as you see. So that completes the first part, all the background information. The next part will be about what happened when we applied this model to the most studied system, P3HT, PCBM, calcium dichlorobenzene now. And what I'll get to is the fact that excitons formed in the fullerene part of this phase, while some of them can diffuse to an interface and be split into an electron in a hole, some of them also can't. So P3HT is this polymer here. It's a thiophene-based polymer, and it's the donor. It has these energy levels. And the fullerene is basically a buckyball coupled to this side group, which makes it soluble and it has a lower energy level, so it can accept electrons. And together, these things form the bulk heterojunction, which is the active layer of the device. So when we use our model and notice a discrepancy between the EQE and the absorption, which results in the IQE, namely, it's not flat. It's flatter. It's lower in the blue end of the spectrum than it is in the red end of the spectrum. So why might this be? Well, as I mentioned earlier, barring some extenuating circumstances, any wavelength dependence in the IQE should come from a discrepancy in the exciton harvesting in the donor or the acceptor. And sure enough, when we look at the contributions to the active layer absorption from the donor, which is the polymer here shown in red, and the acceptor shown in black, it would suggest that maybe there's a problem with the acceptor because the exciton harvesting efficiency is lower where the acceptor absorbs most. So maybe the fusion length is too small in that. So in order to characterize this, it helps to look at the components that make up the internal quantum efficiency. Namely, again, there's the exciton diffusion and charge transfer efficiencies, and then the charge collection efficiency is the efficiency with which those separated charges get out of the device. So for ease of communication, I've grouped the exciton diffusion and charge transfer efficiency into the generic exciton harvesting efficiency, and that is the efficiency at which an exciton formed in one of these materials is harvested in an interface. So when we want to model the IQE, we basically want to know the total current divided by the absorption, and the total current is simply the exciton harvesting efficiency times the number of excitons generated in a material, so in this case the donor, plus the exciton harvesting efficiency in the acceptor times the number of excitons formed in the acceptor, and then all that times the charge collection efficiency, that's the total current, divided by the total absorption. And using this model and the and knowledge of the absorption characteristics of those films, we can fit the IQE curve pretty nicely. And those fit parameters that we fit to show 95% exciton harvesting efficiency in the donor, only 41% in the acceptor, and an 80% charge collection efficiency. And it's important to note that this 95% number agrees with photoluminescence quenching experiments, where we look at the PL from the donor before blending with the acceptor and after blending with the acceptor, and we see 95% emission quenching, showing that 95% of the excitons are quenched. So the fit of this curve agrees with that experiment, which is also it's an independent qualifier. So if the problem is the domain size, then maybe making the domain sizes smaller should help remedy that problem. Sure enough, I've made the domain sizes smaller by casting the films from lower boiling point solvents that will dry faster, so the domains don't have as much time to grow. And as you see, with a faster boiling point solvents, the IQE curves flatten out, and the exciton harvesting problem is solved. Of course, as the domains are smaller, it makes it harder for charges to get out because they need a connected percolating pathway to exit the device. So the overall efficiency goes down as the domains get smaller, but the exciton harvesting efficiency goes up and it's now 100% in both materials. As another check, I've done the same thing, although with the same solvent. The way I make it dry faster in this case is by spinning thinner films. So it's in a thinner film will dry faster. There's less solvent to be evaporated off. And as you can see, as the films go thinner from almost 300 nanometers down to 70 nanometers, the IQE curves flatten out again, indicating that the excitons are again being harvested. So the implications are that in the most studied cell, there's a new type of recombination. The excitons aren't being harvested because the domain sizes are too big compared to the exciton diffusion lengths. And if you were to flatten this curve out while maintaining the total IQE, we'd increase performance by around 7 or 8% for these cells. So now I want to talk about turning that second knob on the IQE, which is the voltage dependence. As you can see, when we increase the bias of the cell and pull harder to get the carriers out more efficiently, we see that this problem is again solved. And this doesn't really make sense because excitons are actually neutral particles. Like they're coulombically bound, and they're small enough that they're actually a quantum quasi-particle with zero charge. So they should not be affected by fields. So this is kind of counterintuitive. Again, we can use the same model to fit the parameters for exciton harvesting efficiencies and charge collection efficiencies in all the materials, and as a function of bias. And as you can see, the PCBM efficiency goes up with bias, even though the charge collection efficiencies and the P3HT exciton harvesting efficiencies remain constant. So this all confirms what we were noticing with the EQE or the IQE curves increasing with bias, but we don't really know why. So a possibility was brought up recently in a science paper by Paul Barbara's lab, which shows that excitons can recombine with electrons via this Auger recombination process I mentioned earlier. What they did was they took a polymer chain, isolated, they added a hole to it in some cases they didn't, and at the same time they generated excitons on it by shining light on it. And what they found was when the excitons were on a polymer chain that had a hole present, the exciton could transfer its energy to that hole and be quenched. And as they change the length of the polymer change, so this happens over some characteristic radius called the energy transfer radius. So as they change the length of the polymer chains and shorten it up, the length of the chain, when it becomes the length of the exciton harvesting radius, or energy transfer radius, sorry, the fluorescence intensity goes down accordingly, all the way down to 0 when they're the same distance. And this shows that indeed excitons can be quenched by carriers. So what would we expect if that was happening? For Auger recombination, recall that, and this is between excitons and carriers now, not between carriers and other carriers, but still it depends on the exciton density and in this case the hole density, but it could be either carrier, a hole or an electron. Because the two-body process, the exciton needs to find the charge carrier before they can recombine. So the rate goes as the square of the total generation, and if we want to look at the internal quantum efficiency, it would start off at 100%, and we add to that the rate of loss of the excitons that are recombining via this process, and so we take the rate of loss divided by the generation rate. That gives us a fractional efficiency. Generation rate and the exciton density are in other words for the same thing. So we divide x squared by x, and we get that the IQE should go as, well, it should depend on light intensity linearly, roughly, 1 minus that. But what happens when you vary light intensity is that between over 5 orders of magnitude, there's absolutely no change in the response of the solar cells. So something's not quite right. The solution to this is kind of a hybrid of that Shapley-Reed-Hall recombination and the Auger recombination, where actually they are recombining with charges via Auger recombination, but all those charges are trapped charges. And in this case, the number of trapped charges is determined simply by the number of total traps, because as you shine light in the solar cell, all the charges that are generated go into those lower lying traps, they fill them up, and then at that point all the extra charges can bubble around on top of those filled states and come out of the device. So since that number is fixed, the rate is fixed, the number of trapped charges is fixed, and now the rate goes simply as the density of excitons, and it's a monomolecular process and does not depend on light intensity. So that all works in that case. So what would we expect? How many trapped charges would we think there would be in the cells? Well, we can sort of analyze this using what is commonly known as the Gaussian disorder model. There's a density of states as a function of energy, and around the bands, there are tails that are assumed to be Gaussian. So we can integrate from the tail all the way up to within kT of the band, and that kT energy is what allows carriers to be mobile. And if we do that, we end up with a total charge density of around 7 times 10 to the 18 per cubic centimeter, which is about 2 orders of magnitude greater than the steady state population of charges in the device under 1 cent illumination. So there are far more trapped charges than there are photogenerated charges in the device, or free photogenerated charges in the device at any given time. So actually, this is quite significant. Why would we expect that the bias would affect the recombination rate? Well, the bias affects how quickly charges can be pulled from the device. And that affects how long those carriers will stay trapped, because the bias can also extract those carriers. So this is exaggerated for clarity, but you can see in this case, under short circuit, I've drawn quasi-Fermi levels to describe the populations of electrons and holes, and the electrons are centered around this quasi-Fermi level. But if you increase the reverse bias, the quasi-Fermi level goes down. In this case, as I've drawn it all the way to the bottom of the band, so that any traps here are populated. Any states above this energy level are not populated. And then in this case, since the level moved down all the way to the bottom, there are almost no trapped charges in that device. And these voltages are far out of our operating range, at least this one is. But that describes the concept. So a way we probed this in our device is by purposefully adding traps. And the way we did this is by putting a very small amount of F4-TCNQ, this molecule here, which is a strong electron acceptor with these homoluminal energies. It's easier to see on a band diagram. The LUMO state is actually mid-gap in the PCBM. So any F4-TCNQ molecules that are stuck in the PCBM phase of this can accept electrons from the PCBM, and because it's so far down in the band, there's no way they'll be able to get out again. These are stuck electrons in the PCBM. And on the other hand, if there's any F4-TCNQ molecules in the polymer phase, this band energy is actually a little bit lower than the HOMO here. So electrons can be transferred from the P3HT to the F4-TCNQ, but they're well within KT. So what the effect is that it acts as a hole dopant in this, creating holes in the P3HT where there were no holes previously. But they're all free carriers because it's within KT of the band edge. So the effect is that we don't really change the solar cell performance too much in terms of the overall cell shape. We do reduce the current because by generating these holes in the polymer, we have introduced space charge, which affects the total amount of current you can get out at a specific bias. But basically, we didn't change the solar cell too much, so that's good. And sure enough, because those trap states are mid-gap in the PCBM and cannot be recovered easily, now the bias dependence of the solar cell has gone away. So now as we increase the bias, we can't remove the traps that we added, and we don't see any more flattening out of this IQE curve. Again, the reason that these curves are still increasing despite their lack of change of shape is because with increasing bias, we do remove that space charge that we introduced in the P3HT, but that is independent of the exciton harvesting efficiency, which would change the spectral shape. So we can probe traps using frequency-dependent measurements. The concept here is simple. This is, again, the Gaussian density of states as reflected by this drawing of states as a function of position. There are more states in the middle than there are at the tails. We use a trapped monochromatic light incident on the cell so that we're alternating between illuminated and non-illuminated conditions. And what happens is that in the light, we generate charges, and they reach a steady state equilibrium with a Fermi level around here, for the sake of argument. And then in the dark, there's no more light on the device. So the Fermi level's new steady state condition will be down here, but it takes some time for these charges to hop out of the traps because these are pretty far apart in energy, and this trap down here needs many KT to get out. So it needs to hop up here and eventually hop up here and hop up here. So over time, those charges will get out, but they'll have some characteristic decay. And what we can do is vary the frequency of a cell, of this chopping, and look at the response as a function of frequency, so that at low frequencies, this decay time is short compared to the period of the chop, and basically you get a square wave, giving the full response, light to dark, light to dark, light to dark. But at high frequencies, this decay rate, the amount of time it takes these carriers to detrap, is much longer than the period of the chop. So now the time period looks more like this, where the effective amplitude is smaller than it would be if we chopped at very low frequencies. And when we do this experiment on devices with different types of fullerenes, it does reflect what we expect from the literature. Namely, the literature shows that C70 variants of the fullerenes in general have more breadth to their Gaussian distributions and have more traps. And as we've seen in the frequency response plot here, the C60 variant shows no shift in the response over all these frequency ranges that we have accessible, whereas the C71 decays as a function of frequency and only levels out really for 10 hertz and lower frequencies. We've also done this on other polymer systems to see what the effect is on the most, this is again the high performance at the time world record efficiency cells. However, it seems that there's no equivalent recombination pathway here, because as we increase the bias, the shape of this curve is not changing. It's only increasing a bit because of other charge collection problems in this cell. But for this device architecture, PCD-TBT, and also with cells made from MEH-PPV, they don't show this effect. And in fact, no materials we've tried this on, aside from P3H-TPCBM, show this effect. And so this is an interesting result, and I don't have a firm answer for it, but I would believe that the reason is because these materials, and most materials used actually, show intercalation, where the fullerene forms a bimolecular crystal with the polymer. So the fullerene molecules can get integrated into the polymer, making a new effective material. And therefore, any excitons formed in the fullerenes can immediately be split at the polymer interface, because every fullerene is next to a polymer. So it kind of makes sense in that light. It could also be morphological. Maybe these devices just have smaller domains. So we also wanted to check into whether this is a problem for polymers in general, not just blended polymer fullerenes systems. So what we did was make polymer-only diodes, and I've shown here the JV current response and also on top of that, the photoluminescence at that bias. So photoluminescence is here on the right in black, and the current voltage, and the current is shown on the left. And you can see that wherever the current is flat, in this case, the photoluminescence doesn't really change. Whenever we start injecting charge into the diode, the photoluminescence goes down, showing that indeed when we have charge in the device, the excitons formed don't luminesce as well. Their lifetime goes down because of recombination with these free carriers. I also made a diode with this F4TCNQ trap additive, which is actually mildly trapping charges in the P3HT, in this case, making holes. And the interesting thing here is that in the region where there's no injected charge, we still see dependence on the photoluminescence. And in this case, the photoluminescence actually goes up with reverse bias and slightly more charge injected. And the reason is because as we increase this bias here, we're not injecting charge, but we are extracting those trapped charges that we added purposefully. And again, showing that the photoluminescence lifetime, the non-radiative recombination lifetime is increasing. And so now photoluminescence can compete with that, and the PL efficiency goes up. And this is true of those other two polymers I mentioned earlier as well. So it does seem to be a general effect. But this requires more research. And as such, future research might include trying to generalize this in a strong way to show that for all of these high-performance weakly emitting polymers, the reason they might not be performing so well is because of this Auger recombination process with trapped charges. And if we could fix that problem, it would greatly increase the performance of these devices, because we could get better charge transport in the devices by allowing for larger domains. Larger domains always give you better charge transport. Because the charge transport's better, we'd be able to make the films thicker, allowing for more absorption of the solar photons. So we'd get more total current. And also, with larger domains, this opens up the possibility for nanoscale patterning. Right now, with 5 nanometer diffusion lengths, we can't really, with current lithography techniques or even fancy patterning techniques, manually make structures on that scale. But if we could increase the diffusion lengths to 10 or 20 nanometers, all of a sudden, those options become more viable. So this could be quite important in the future. So in summary, we've developed a technique for accurately measuring IQE and publishing the first flat IQE curves in the literature. Using this technique, we've identified a new recombination process in the most studied system, P3HT-PCBM, where the fullerenes are not harvesting all of their excitons because the diffusion length in the fullerene is too short compared to the domain sizes. And we determined that the reason that this happens is because excitons are recombining with trapped charges in the fullerenes. So with that, of course, I'd like to make some acknowledgments, because this stuff is never a lone process. There's lots of people that had hands in this. First of all, I'd like to express my great gratitude to my committee. It's been quite a hectic procedure trying to organize this, and especially Stacy Bent, who agreed to join the committee as of Monday when we realized we had a problem with the original setup. And especially during finals week, it's such a hard thing to find a faculty member who's available. So I really appreciate that. And of course to Michel Digonet for coming out. I really appreciate your, oh, that's not a problem. I'm glad you're here. And despite the fact that we hadn't really met before, I really appreciate your presence anyway, because this is very important in the process. Alberto, you've been a great friend. It's always great having you at the end of the hall. And of course, your lab is awesome to hang out with Rodrigo and Leslie and everyone over there. Even though we haven't hung out that much personally, I always enjoy our conversations. It's always hilarious, and I also get to hear all kinds of great stories about you from your lab mates or from your students, which maybe you don't really know about, but we can talk about that some other time. And of course, Mike, my advisor, and Ian, my co-advisor, have played a much more, well, not to be comparative here, but they played a significant role in the research over the past years. Ian's kept me on track, asking me from time to time what I'm up to make sure that what I was doing was actually going to qualify for an applied physics PhD and not just making machines in the lab for fun. And which, to be honest, I actually do have a lot of fun doing that, and it's a good thing to keep me on track. And so that's very important. And then, of course, Mike has had a guiding hand in everything I've done. From the initial project of Exciton fission, which I kind of mentioned in one slide there. I was actually working on that for the first couple of years here. Didn't quite pan out. But sure enough, Mike's always been very supportive in letting everyone in our lab do pretty much what we want. And so I picked this project up from Sean Scully, who I'll mention in a second. And since then, we've discovered a lot of interesting things and a lot of the great things I've learned about how to do research, and most importantly, how to present research, has come from Mike. And to get off the research topic for 1 second, I have to say that when I first got here, I started writing when I was at Yale, but there was a lot of classes, and I didn't really have that much time to do any racing or anything like that. And when I joined the group, we don't have the fancy bike rack we have now, but there were a lot of bikes in the front office. And so every day I'd come in there and add my bike to the stack, and eventually the stack grew to the point where we couldn't open the door anymore. And Mike and Morgan Mayer from I forget which group he's in now.
Melocious.
Oh, it's a Melocious group. Yeah, I knew he was either Melocious or Grisma. Anyway, Morgan and Mike put together this bike rack so we could fit 7 bikes in our lab. And since then, we've had lab rides. I started riding more and more, got interested in the cycling team and started riding with them. And I'm getting kind of out of order, so I'll leave it at that. But again, I started riding with Mike on Old Honda. Mike used to beat me all the time. And eventually I got fast enough that I could beat Mike. So I'm happy to have that be the one person that could beat you. Of course, I'd like to thank the rest of my group who's had the most hand in my research, and especially, so I don't want to list everyone there because it would make this too long, and I don't want to leave everyone out. Because there have been people in and out during those times. So I'm going to list the people who've had direct work in the research, namely Eric Hoke and Zach Bailey, listed here, or shown here. Zach's quite the musician, and Eric is quite the model in his Cambridge getup over here. Eric's been on all my papers and has helped. We've actually pretty much done most of this stuff together, and aside from the fact that I was repeating the measurements a lot of times, Eric helped me put all these measurements together, think about the problems with the research and what to do to fix them. And so this is almost I would say it's as much his work as it is mine. The only difference being that Zach played some role in this too, which is that Zach is the trap expert. And over the first 3 years now, three years, Zach's been becoming an expert in traps in these materials. And so when it turned out that these excitons were recombining with traps, he was the guy to go to. And he's the one that gave me the idea to use the F4TCNQ molecule, which provided like the entire last chapter of this thesis and the last paper that we're going to publish on this. So thank you very much, Zach. Anyway, And of course, as Mike mentioned earlier, I published a few papers with other groups, namely the Shui group. Qingmei and Jia are here, or Jia's not here, but Qingmei's here. Thank you, Qingmei. Until yesterday, I hadn't published a paper with Whitney, but now, as of yesterday, I heard that that paper was accepted, so I should have added your name here. I just didn't think to do it. I'm sorry. But Whitney deserves special thanks to here, too. And okay, so Justin Brockman, Dave Bernstein, Melissa, and Matt, who I think are all here, deserve special credit for keeping me in grad school. The first couple years we were here, we were taking classes, and it was very stressful. And basically, every time we had homework to do, we would do enough of the homework that we'd pass. We'd spend the rest of the time drinking wine and eating food and just hanging out. And that process kept the pressure down low enough that after the second year, when I was about ready to quit, I was like, okay, the light's at the end of the tunnel. I can make this, and sure enough, I finished up classes and I got to do research. So without you guys, I would not have been able to do that, that's for sure. The Sam Recycling team has provided much of the, not only their presence here, first of all, at the front and the back in droves, but a lot of additional decompression required over this time, and also the ability to beat Mike up over Honda.
Wait, did you get faster or did he get slower?
I'm going to say that I got faster, just because Mike probably wouldn't like it if I said he got slower. But also, but to be fair, I did increase my time by about 5 minutes over those years, so I got faster. Mainly thanks to these guys. And also, they provided a great friend base and lots of extracurricular time. And so of special note is Elizabeth Shem, who has been not only a great source of emotional and moral support, but also has done a lot of the work in the background for this type of project. She edited my entire thesis, and she's also read a lot of my papers and helped me out with all the wording and graphs, and she's really great at communicating. So in terms of making slides and things like that, she's been a great help. And then, of course, a lot of the food you enjoyed so far as a result of Liz's work, both in the kitchen and also, carrying pots of coffee and trucking things around to make this all possible. So thanks, Liz. And of course, my mom and my brother. My mom is here. My brother couldn't make it. He's got a rather busy job in New York in investments. But they both played a great role in bringing me here now and making me who I am today. And of course, my mom also was around to help out. I don't even know who she is. To help out with the refreshments as well. So everyone else can thank her as well. So with that, thank you all for coming, and that's it.
Okay, we'll have some questions from the public before we go to the private part of the exam. Who wants to be first?
Craig.
Did you ever try this study with PBTTT, another sort of crystalline polymer?
No, actually I haven't. That would be interesting to do. But it does... It intercalates. Yeah. So that would be an interesting way to test the crystallinity aspect versus the intercalation aspect. Yeah. Anyone else? Brian?
Two-part question. The first one is, how does the difference in the domain size between the donor and acceptor, are they different? And how do you think that affects the IQE performance? And then the second question is, do you think it's a really good idea to harass your advisor before you go to the private course?
Well, I'll answer the second question first, which is, maybe he'll just focus on the harassment and not on the thesis. And to answer your first question, the domain sizes are actually kind of hard to characterize. There's been a lot of work with transmission electron microscopy, but unfortunately, it's really hard to get proper contrast between the two because there's actually a few materials present. If you think about the fact that P3HT has a crystalline phase and an amorphous phase, and the amorphous phase of P3HT has the same contrast as the fullerene phase does. So you really can only see the crystalline phase. And the same thing is true if you want to take, it's not even a good idea to take AFM images to probe deep crystal structure, but if you did, you'd see the same sort of thing in the phase aspect of the AFMs. And so anyway, it's hard to tell exactly how big each of those phases is. But given the fact that P3HT forms these long needles, I would say that the total volume per crystallite of P3HT is probably bigger than the total volume per domain of PCBM, but they're long, thin crystallites. So that might not actually be a problem for exciton diffusion, because although there's total volume, the surface area to volume ratio, it's got a high aspect ratio. So I think there was a question over here somewhere. Maybe. Chris?
Yeah, so you showed that by reducing the domain size, you're able to flatten out the curve, the IQE curve, but it reduced the overall efficiency.
Right.
But then by having a thinner film,
Yeah.
that you can improve that. Would that be the solution, have a thinner film, or is there some other way to apply that?
So unfortunately, no. So these are plots of internal quantum efficiency. So the electrical characteristics of the cell do get better with thinner films, but with the thinner film, you're not absorbing anywhere near as much light. So the total efficiency of the cell goes down. And as far as optimization with like film thickness and solvents goes, the devices I started off with that had the slanted IQE curves are the most optimized devices that they have. Those are a bit over 4% efficient. Those other devices, although they have better internal quantum efficiencies, are overall much less efficient, probably around 2%. So, yeah. Craig or Jason?
I had one question. On the graph that you were showing the effect of reverse bias on the exciton harvesting efficiencies for P3HT and PCBM, as well as the charge collection efficiency.
Yes.
It seems like the charge collection efficiency doesn't really change
Right.
with reverse bias, but I was kind of surprised to find that if you supposedly increase the field, you don't actually
Yeah.
get
So
any better.
that's mainly because P3HT PCBM is a really great system for transporting charge. They both have really high mobilities. So any charges generated in the film, even at 0 volts and even at forward voltages below VOC, they can all get out without a problem just based on the built-in field. So pulling harder on that doesn't really help. The other part of the charge collection efficiency, of course, is the geminate recombination rate. But that also is not affected by the field very much, because after charge separation, although the exciton and hole are still related to each other somewhat, they're still slightly bound, and most of the energy that comes to separate them comes from the thermal energy, just diffusing away from each other. The field, although it's a pretty significant field when you think about field strength, it doesn't provide that much additional energy compared to the thermal energy and the chemical potential offset that are already present in terms of separating those charges. So increasing the field doesn't really help that very much. Okay?
So on the plot, the IQE of the P3HT cell drops off at redshifted wavelengths.
Yeah.
Is that an artifact of the measurement, or is it telling you something interesting about
No,
space
so
and band gap?
right here, like right here, it's drop off.
Yeah, you showed it on your other plots as well, when you actually had a flat
Yeah.
IQE, but it dropped off as you...
Oh, you mean this one on the
Yeah.
bottom?
Exactly.
Yeah. So it's kind of a mixture. On the one on the bottom, it's mainly just a defect in the measurement. The measurement works by the approximation that the active layer is doing almost all the absorption, and then because of that, we can model only the parasitics and subtract them from the total absorption. And in the areas where the active layer is doing most of the absorption, this is true, and it's a valid estimate of what's going on. But as we get towards the band gap, the active layer absorbs less and less, and the parasitic absorption matters more and more. And so those errors in the modeling start to matter more and more, and we start getting more sensitivity to the modeling error. So that's the main thing. But I would like to point out here that at low
wavelengths, the P3HT is absorbing, and this is actually almost a little bit of a defect too. The P3HT should actually almost go to 0 here. The PCBM is actually doing most of the absorption at low wavelengths, despite the fact that, that the P3HT does more in the mid-range. So this tail here eventually starts going down a bit more, but the modeling error kind of prevents accuracy. But that also is due to the fact that the P3HT or the PCBM max tails aren't being harvested. You can see that in the blue and the deep red. Al?
So one of the last few slides you mentioned about fixing the Auger recombination and how that could lead to better solar cells. Is that more of a new materials design aspect, or is it the processing, or like how would you separate off?
So
what could be done in those areas to invent
There are probably clever ways to do it, but at first glance, I would say the way to do it is just make materials that form, that when deposited, form structures that have narrower trap distributions. So these traps are usually formed by twists in the polymer chain, causing different overlap in the pi orbitals, or if it's in a fullerene, the way the fullerenes are oriented with respect to each other. So if there's a way to get self-assembly that's more uniform, then there'll be less energetic disorder in the materials, and those Gaussian distributions will be more narrow. And hopefully, if they're narrow enough, then all those traps will be within KT of the band edge, and you won't have any traps. Even if they're not that narrow, the tails will be very few, so that should improve the problem. Eric?
So it seems like in a lot of this work you assume that the field varies linearly between the two electrodes, but these materials are intermixed,
Right.
and they're not,
Yeah.
it's not like a bilayer or
Yeah.
even an even blend. I'm wondering how valid that assumption is.
So actually, we
Are there
didn't.
field variations within the...
Yeah, so there are definitely field variations. It's not because of the fact that they're blended so much as the fact that there's more charge near the electrodes than there is in the bulk. And charge collection can also depend on, that the mobility might be higher in one section of the material versus the other. The most important thing is that we do all this stuff at 0 volts or a negative bias. So actually all those charge distributions really aren't there anymore because the device is fully depleted at those biases. And we can show that using impedance spectroscopy or actually capacitive voltage measurements to show what the width of the depletion layers are near the metal contacts. And so at 0 volts and at negative bias especially, you pull all those charges out and the field is constant across the device. But most importantly, none of this really hinges on the field characteristics because although the field determines the quasi-Fermi level in the device, it's really the total population of charge that matters. It's the total voltage drop across the device that really matters for that. And you might have a section where there are some more traps because there's more traps in that section of the device, and therefore more charge there. But for the bulk behavior, we really care about the total number of traps. And so that's mainly set by the generation rate and the bias conditions.
Okay, if there are no more questions, let's thank George again.